Electromagnetic wave. You see, the idea of electromagnetic wave was introduced by scientist Maxwell. He considered the light as electromagnetic wave which doesn't require a medium for its propagation. To understand the basic phenomena of electromagnetic wave, one always needs the detailed description of displacement current. Conduction current you are already familiar with. That is a continuous current because of the conduction electrons, continuous flow of charge carrier. But in condenser, between the two plates, you see, there is gap, there is air gap. So obviously at first instance, one would feel how the current is possible between the two plates. But when the condenser is getting charge in that case, here on one plate, suppose positive charge is developed, then because of induction here the negative charge is developed and other side of the plate being positive, producing positive charge will be responsible for flow of that positive charge. Charge has flown from one terminal of the cell to one plate and charge will flow from other terminal of the condenser to other plate, other terminal of this cell. That means the charge is flowing through this cell, and here, despite the fact that there is gap between the plates, the charge has maintained its flow through the cell. This way of current is known as displacement current. Here we say that displacement current is flowing through the condenser. Its value of displacement current is given by this relation ID, that is equal to epsilon naught. Epsilon naught is permittivity of free space. This relation is given for displacement current. Here phi stands for electric flux. This is known as displacement current. Ampere-Maxwell law. Simple Ampere's law is integral BdL. This is equal to mu naught I. This is Ampere's law. But if you add displacement current also, it becomes Ampere-Maxwell's law. Means Ampere's law stands only for the conduction current, but along with conduction current, when you sum up displacement current also, then it is generalized and becomes common for all. That means for both conduction and displacement current. You see, Maxwell took the help of four theories together to formulate the framework of electromagnetic wave at length. He took the help of four theories that are given one by one over here. Gauss' law for electrostatics, that's given by EdA equal to Q upon epsilon naught. This law confirms Gauss' law for electricity. It confirms that charges can exist as a monopole. From plus charge, the electric lines of force start. At minus charge, electric lines of force terminate. Moreover, electric lines of force can be as open curve. This was confirmed by this Gauss law itself. But when it comes to magnetostatic integral, it is surface integral BdA equal to 0. It simply means that monopoles in magnetism cannot exist. That is, magnetic north or magnetic south cannot exist independent. They are always dependent. Interdependent means whenever they exist, they'll exist together, not as a single pole. And magnetic lines of force are always closed curve. Here we say emerge from north and enter through south. Whereas for electricity, we say start from plus charge and stop at minus charge. Then what is Ampere's Maxwell law? I told you right now. When you take both the current, it becomes Ampere-Maxwell law. And for ID, you could write down epsilon naught d phi E upon dt that we have replaced over here. And finally, fourth theory of electromagnetic theory is, fourth point is Faraday's law used in electromagnetic induction, that says integral E dl equal to minus d phi dt, but here the flux is that magnetic. Rate of change in magnetic flux is equal to the EMF induced in the process. That is what we call Faraday's second law for electromagnetic induction.